This is what we call the snake lemma, and part of the snake lemma is defining this map D, a map that goes from the kernel of C all the way down to the co-kernel of A. And we define that map through what we call diagram chasing. So let's do some diagram chasing and define that map. So for an element of kernel of C, I'm going to define an element of co-kernel of A that maps to it. So we start with an element of the kernel of C. That means an element here that maps to 0. Since this is exact, this is surjective, so there's some element here that maps to that element here. There may be more, we'll talk about that later. But there is one that goes here, and since this is a commutative diagram, if it goes from here to 0, it also goes from here to 0. So take that element, send it here, it goes to 0, so it's in the kernel of this map. Since this is exact, there is an element here that maps to that one. And since this is injective, there is only one element that maps to that one here, so take that element and send it to the co-kernel. That's the definition of D. Now, what happens if there are two elements here that map to the same element here we started from? Well, then their difference is in the kernel of this map, but the kernel of this map is the image of this one. So there's an element here that maps to the difference, and that element from here to here would map to the 0 here because that's the co-kernel of this map. So if there was another element here and you traced it back here, they would both map to the same element here. So the map D, so defined, is well defined.